Have you ever really thought about how wild it is that medical professionals can literally switch human consciousness off and, crucially, turn it right back on again? Welcome to This Explainer. Today, we're tracing the exact physical path of an anesthetic gas molecule. We're going to follow its journey all the way from the anesthesia machine deep into the human brain. It is absolutely a modern medical marvel. And to truly understand it, we've got to follow the molecule every single step of the way.
I mean, it really feels like the ultimate magic trick, doesn't it? You breathe in this sweet-smelling gas, and moments later, you're entirely unaware of major surgery. But behind this apparent magic is this incredibly fascinating, highly structured physiological race. And it's a race strictly dictated by partial pressure gradients and tissue solubility. The main thing to keep in mind here is that this isn't random. It is a carefully orchestrated molecular cascade.
And, we've actually been perfecting this exact process for nearly 2 centuries. Starting way back with Crawford Long using ether in 1842 and Horace Wells with nitrous oxide shortly after, we have constantly been searching the chemical world. The goal has always been finding agents with faster, safer, and just more reliable pharmacokinetic properties, which eventually led us to modern mainstays like desflurane and sevoflurane.
Now, to really grasp how this all works, we have to look at pharmacokinetics. That's literally just a fancy way of saying what the body does to the drug. We need to follow our anesthetics journey from the fresh gas flow in the breathing circuit down into the alveoli of the lungs, straight through the arterial blood, and finally across that blood-brain barrier.
So the journey kicks off right at the anesthesia machine. The vaporizer takes the liquid anesthetic agent, turns it into a gas, and the fresh gas flow pushes it down a concentration gradient. Because you've got a massive concentration of gas in the machine and absolutely zero in the patient's lungs, the laws of physics essentially dictate that the gas is going to rush directly into the patient's alveoli, those tiny air sacs in the lungs where gas exchange happens. The absolutely critical concept here is alveolar concentration, or FA. Our main objective in anesthesia is to establish a specific partial pressure of the drug inside the patient's brain. But, well, since we obviously can't just stick a sensor inside a living human brain, we rely on FA. The gas concentration right there in the lungs acts as our primary, real-time surrogate for what's happening up in the brain, and therefore the depth of the patient's anesthesia. But here is the catch. To get from the lungs to the brain, the gas has to cross the bloodstream. This is its biggest hurdle. Blood solubility. Think of the blood as a sponge and the brain as the soil waiting for water. High-solubility anesthetics are like extremely absorbent sponges. They trap the drug in the blood, creating this massive pharmacologically inactive reservoir. That drastically slows delivery to the soil, meaning a super slow induction. On the flip side, low-solubility anesthetics are less absorbent sponges. They saturate really quickly, allowing the drug to rapidly spill over and reach the soil of the brain way faster, which gives us a rapid induction. This whole dynamic sets up a literal physiological race. If we look at the ratio of alveolar to inspired concentration over time, those low-solubility agents, our less absorbent sponges like nitrous oxide and desflurane, they just shoot straight to the top. The blood fills up fast, and alveolar concentration rises incredibly quickly. Meanwhile, highly soluble gases like methoxyflurane just get hopelessly left behind, completely trapped in that blood reservoir. We actually quantify this exact sponge-like behavior using a number called the blood gas partition coefficient. Take halothane, for example. It has an incredibly high coefficient of 2.4. That literally means you need so much more of it just to saturate the blood before it can ever even think about reaching the brain. Now compare that to nitrous oxide at 0.47 or sevoflurane at 0.65. Those reach a rapid equilibrium, allowing the provider to put the patient to sleep much, much more efficiently. Okay, so once the gas finally saturates that blood sponge and breaks free, it distributes to the tissues. But it doesn't do it evenly. It strictly follows the blood flow. The brain, which is part of what we call the vessel-rich group, is the very first tissue compartment to equilibrate with the gas. It spikes way, way before the muscle or fat groups even get a chance. So why exactly does the brain win this race? It's all because of the vessel-rich group's incredible blood supply. We're talking the brain, heart, kidneys, liver, and endocrine organs. Even though this group makes up a measly 10% of total body mass, it receives a massive 75% of the cardiac output. So it aggressively soaks up the anesthetic first. And just like lipophilicity, think about how readily water spreads through the soil directly to a plant's roots, or in this case, the brain receptors. Highly lipophilic drugs move so much faster through the lipid membranes of the brain once they leave the blood reservoir. This puts the patient to sleep rapidly while the fat and muscle are just slowly absorbing the leftovers.
All right, with the molecule finally in the brain, how do we actually measure its potency? We use a gold standard measurement called MAC, which stands for minimum alveolar concentration. Simply put, this is the exact dose required to suppress movement in 50% of patients in response to a painful stimulus. It's a brilliant way for us to directly compare the strength of entirely different anesthetic gases. And MAC possesses some truly mind-blowing properties. The standard deviation across the entire human population is remarkably tight, just 10%. That means at 1.2 MAC, 95% of all patients will not move. Plus, MAC values are perfectly additive. You can literally take half a MAC of nitrous oxide, add it to half a MAC of isoflurane, and boom, you get a full 1.0 MAC clinical effect. This uniform inhibition of our spinal cord reflexes is entirely unaffected by the patient's gender or even how long the surgery lasts. Now let's transition from pharmacokinetics over to pharmacodynamics, which is what the drug actually does to the body. Here we see exactly how the gas depresses the central nervous system. It basically enhances inhibitory ion channels like GABA receptors, while physically blocking the excitatory ones like NMDA receptors. And different parts of the brain map to different effects. The cortex and brainstem handle unconsciousness, the amygdala is responsible for amnesia, and the spinal cord controls immobility. But how do these specific receptor changes actually erase consciousness? That's the million-dollar question, right? While the exact nature of human consciousness is still one of science's greatest mysteries, researchers believe these gases wage a sort of dual attack. The bottom-up theory suggests they completely suppress the fundamental sleep-wake arousal centers deep in the brainstem. At the exact same time, the top-down theory suggests they disrupt the transfer of information across the frontal parietal network in the cortex. So the brain simply stops communicating with itself. The coolest part? As an anesthesia provider, you aren't just some passive observer to this molecular journey. You can actively manipulate it. For instance, intentionally dialing up a massive initial dose of gas creates what's called the concentration effect. By absolutely flooding the system, you overpower that blood solubility hurdle we talked about earlier, which radically accelerates how fast the patient falls asleep. Okay, so the surgery is a total success, and now it's time to wake the patient up. How do we do it? Well, it is essentially the exact inverse of induction. We turn the vaporizer off, dropping the inspired concentration to 0. This completely reverses the partial pressure gradient. Now the gas is forced to flow out of the brain, back into the blood, and is transported to the lungs where it is literally just exhaled away.
But as you might guess, waking up isn't always instant. Remember those muscle and fat compartments? Throughout a long surgery, they've been acting as high-capacity sinks, quietly absorbing the anesthetic the whole time. When we try to wake the patient up, those tissues start to slowly leak the anesthetic back into the blood. If a highly soluble agent was used, this prolonged leaking can significantly delay a patient's awakening. And that's exactly why drug choice and understanding solubility is absolutely critical for a smooth recovery.
This entire intricate journey from the vaporizer through the blood sponge and deep into the lipid membranes of the brain really highlights the profound, beautiful complexity of anesthesia. And it leaves us with this wild question. As fMRI and imaging technologies get better and better, visualizing exactly how these molecules disrupt our neural networks, are we on the brink of finally decoding the precise anatomical map of human consciousness itself? Are we going to one day look at a monitor and literally see the depth of a human soul turning on and off? Definitely something to think about. Thanks so much for joining me for this explainer. I really hope this helped illuminate the incredible science of inhaled anesthesia.